Good afternoon, ladies and gentlemen. Today we'll be focusing our energies on sample proportion. So we'll be looking at the proportion of a sample that fits a certain criteria. We saw this in the previous video when we were taking samples of Reese's Pieces, and we recorded the proportion of those samples that was orange and then recorded a sampling distribution. So what can we do? We should be able to find the mean and standard deviation. We should decide if we can use a normal approximation, and we should be able to calculate probabilities and evaluate claims about a population's proportion. So here we go. Sampling distribution of p hat, the proportion. How good the statistic p hat is of an estimate for the parameter p, we're going to look at the Reese's Pieces again. I've got some screenshots for when the population has a proportion, say that 10 times fast, the population has a proportion is either 0.45 and 0.15. And we're going to look at the shape, center, and spread of each of them. So here are two samplings where the population proportion is 0.45. Notice the difference. The left one we're sampling at 25 items, and the right one we're sampling at 50 items. Notice that the center of this distribution is at the population proportion. Notice that the standard deviation gets smaller as the sample size gets bigger. Here we are with a population proportion of 0.15 for both of these. Notice again the mean of my sampling distribution is centered at the population's proportion, and when the sample size is 50, we're again centered at the mean. We're using pi instead of p, but our p hat is centered. The average value of them is remaining the same. So, what are we seeing? With both of these cases, the sampling distribution of p hat can be approximated by a normal curve. Those distributions look mostly normal, symmetric, bell-shaped. However, the overall distribution depends on both the sample size and the population proportion. That bell curve moves and changes its height and width and spread depending on the population's proportion and the sample size. The mean of our distributions, the mean of our p hats, is equal to p, pi in that case, the population proportion. And sample proportions, p hat, those are going to be unbiased estimates of our population's proportion. The spread, as p gets, for each value of p, the standard deviation got smaller and got bigger. And that is something that's always going to be the case. The bigger the sample size, the smaller the standard deviation will be. The value of sigma, the value of our standard deviation of the sample proportions, depends on both n and p. So our sample size and our population proportion changed the overall spread of our data. So basic formula here, our p hat is the count of successes in a sample divided by the size of the sample. So it's x divided by n. Remember from last chapter, x was a random variable. It was the number of successes in each trial. So we're relating what we're doing here to our probability distributions. And let's take this a little further. In chapter 6, in the previous section with random variables, we found that the mean of a random variable is n times p. The standard deviation of that random variable is np times 1 minus p square rooted. But since p hat can be found by taking the number of successes divided by the sample size, we could think of that as being 1 over n times the random variable. Therefore, the mean of our sample, the mean of our sample proportion is equal to 1 over n times np, mean of our random variable. Well, 1 over n times n is just p. So the mean of our sample proportion is equal to the mean of our population. And that should make sense if we take enough samples. If we take every possible sample, if we have a sampling distribution, a true sampling distribution where we have accounted for every possible sampling of that size, we will have our mean equal to the population's mean. And we can develop a formula for standard deviation of our sample proportions. 1 over n times the mean of our 1 over n times the standard deviation of our random variable. We can rewrite that in this way. P times 1 minus p over n. And what this means is as the sample size increases, the spread decreases. Should make sense, ladies and gentlemen. So, there we have it, and here's a nice summary of this. If we're choosing a simple random sample of size n from a population of size capital N with proportion p of successes, let p hat be the sample proportion of successes. Then the mean of that sampling distribution, mu sub p hat, is p. The standard deviation of our sampling distribution of p hat is found with this formula as long as the 10% condition is satisfied. As long as the number of things in our sample is less than or equal to 1/10 of the population size. We saw this last chapter for our test in independence with the binomial distribution. As n increases, and we saw this with our sampling of Reese's Pieces, as n increases, the sampling distribution becomes approximately normal. But before you perform normal calculations, you must make sure that, just like last chapter, n times p is greater than 10, and n times 1 minus p is greater than or equal to 10. If that's the case, we can use our normal distribution funness. And yes, that is not a word, ladies and gentlemen. So here we have a visual summary of what we've just discussed. We have a population of items, and in that population there is a proportion p of successes. We are going to sample repeatedly a simple random sample of size n, and from that sample calculate our sample's proportion. And if we do that enough, our dot plot, our visual representation of those population samples proportions, begin to resemble a normal distribution. And we can calculate the mean, it's the same as p, and our standard deviation, and perform normal distribution calculations. And that, ladies and gentlemen, is the big idea behind this section, and here we go. So, we are making inference about a population's proportion, and it's going to be based on the sampling distribution of p hat. When a sample size is large enough for np and n times 1 minus p to both be at least 10, that's what we call the normal condition, the sampling distribution of p hat is approximately normal, and we are going to use that in this example. So a polling organization, this is used all the time with polling people, because we can't poll everybody. We're going to ask a simple random sample of 1,500 first-year college students about how far away their home is. Suppose that 35% of first-year students actually attend college within 50 miles of their home. So 35% of all first-year students will attend school within 50 miles. What is the probability that the random sample of 1,500 students will give a result within 2 percentage points of this true value? So here we go. Let's look at this. State, what are we looking for? We want to find the probability that the sample proportion falls between 0.33 and 0.37. That is 2 percentage points of 35%. plan? Well, we have a simple random sample of n equal 1,500. We're taking that from a population in which the proportion of success is 0.35, attending college within 50 miles of home. So that means that the mean of our p-hats is 0.35, and our standard deviation of our p-hats can be calculated and found to be 0.0123. And we can use a normal distribution because NP and N1 minus P are both greater than 10. And so we can standardize using z-scores and then use table A, or we can calculate this in our calculator. Using table A, we get these two z-scores. We look those up. Z-score of 1.63 gives us a probability of 0.9414. Z-score of negative 1.63 gives us a probability of 0.0576. So our probability that p-hat is between those two values is 0.8968. So what this means, the fourth step of our four-step process, is that about 90% of every simple random sample that has a sample size of 1,500 will give a result within 2 percentage points of the truth of our population. And that, ladies and gentlemen, takes us to the end of this section. And here is a summary of everything that we just looked at. And in the next section, we will look at the sampling distribution of means.